Hi, my name is Matt Ruffner, and the title of this talk is Community Graph Sampling as a Vaccination Strategy. The spread of information or disease across a population or network has been widely studied in network science and epidemiology. The terms immunization and vaccination are used interchangeably and refer to the process of selecting nodes to remove from the susceptible portion of a population. In other words, the infection or information can no longer spread through an immunized node. Choosing which nodes to vaccinate is a node importance problem for which many so-called centrality metrics have been developed. Through simulations, I will show which centrality metrics prove useful and effective as a vaccination strategy and how performance varies for different network types. I am particularly interested in the application of graph sampling to this problem, since selecting nodes for vaccination is by definition a sampling problem in the graph domain. To give a little background on the SI and SIR epidemic models, the population is divided into at least two groups representing susceptible and infected portions. Seminal models for simulating epidemics used homogeneous mean field approaches that assume every member of the population has an equal likelihood of interacting with one another. Intuitively, this is not the case for real-world social interactions. You can see that as time progresses, the susceptible portion of the population decreases to zero, while the number of recovered individuals increases proportional to the integral of the infected curve. To account for shortcomings of these models, one approach uses a synchronous cellular automata approach based on discrete time Markov chains. This simplifies simulation implementation and allows for easy operation on a graph specified by an adjacency matrix. For this work, I am considering simple graphs which are connected and undirected. To this end, my work focuses on evaluating vaccination strategies as well as simulating the spread of a disease across these networks in a way that takes into account varying structural and topological properties. Below is an example of a simulated diffusion process across a simple community graph. You can see the number of yellow nodes representing the infected individuals increasing with time from left to right, where at each time step, each node has a 50% chance of getting infected from any of its infected neighbors. 6 widely used centrality metrics of varying computational complexity are calculated for 3 different networks. Betweenness correlates to the number of shortest paths which are incident upon a vertex, while current flow betweenness, also known as information betweenness, reflects path lengths in terms of random walks on the graph. Closeness is inversely proportional to the sum of distances from a given node to all other nodes, and eigenvector centrality represents a node's importance based on the importance of its neighbors. These centrality metrics are evaluated on both simulated and real-world networks. LFR models were generated and used with parameters consensual with literature in addition to the Europe email dataset and Facebook Ego Circles dataset from the Stanford SNAP repository. A quantity known as prevalence is used to judge the effectiveness of the centrality metrics as a vaccination strategy. This quantity represents the fraction of infected individuals at the end of a simulation. The 1,000 node generated LFR network was the sparsest of the 3 tested networks with the lowest clustering coefficient and number of edges. With limited paths for diffusion in this model, none of the evaluated methods are able to significantly decrease the infection prevalence with respect to the proportion of initially immunized nodes. In the email EU dataset, it is evident that a higher clustering coefficient and connectivity enables a more effective vaccination strategy. All strategies except random are still grouped together, however, with no significant improvement in performance between any 2 metrics. The Facebook Ego dataset is the most receptive to vaccination, with betweenness and current flow betweenness able to reduce the infection prevalence more than 80% by immunizing less than 10% of nodes. Moving forward, I plan to utilize the simulation framework I've developed to evaluate improved modular centrality metrics as well as existing graph sampling methods to determine their effectiveness as a vaccination strategy. Thank you.